Hello, my name is Daniel Reagan, and today I'll be presenting biomedical engineering problem solving in Python. Now, first up, why use Python? Well, Python allows you to compute problems faster, you can reuse your code for multiple problems, and it will remove human error that you could have solving something analytically. So for our first example here, the drug is administered intravenously with an initial concentration C0 in the bloodstream. Concentration decreases according to the function showed here. C of t equals C0 times e to the power of negative kt, where k is the elimination constant. Now, in this example, we're going to time value of the concentration dropping below a certain concentration, and we're going to graph the concentrations decay. So for this first part here, you can see trying to solve this analytically doesn't look too hard. You just plug in the concentration and you solve for the time value. But in Python, it gets a lot easier because we just plug in our initial condition in our k value and the time we want to get to. And you can see here we use BrentQ, which is a root finding method. It's similar to Newton-Raphson. And as you can see here, we got that exact same time using this. And it's only a couple lines of code rather than algebra. In the second part of this problem here, graphing it, you can see here our graph starts at 50 concentration and it goes all the way down to about 1, a little bit above 1 after 24 hours. And in Python, a similar thing here. You can see the graph looks very much the same, and it's just some code. As you can see to the left here, we have the colors and tables and all that good stuff there too. Now, moving on to the second problem, concentration of a drug in a bloodstream C following an intravenous bolus injection is often modeled as a two-compartment model, so similar to this previous example, but this one has two separate things. T is the time in hours, A, B, alpha, and beta are the different parameters of the specific drug. And also using this, we can also find the area under the concentration time curve, also denoted as AUC, which is important to measure exposure from the time value to the final time. As you can see from that, it's finding the integral of it. And in this example, we're going to find different concentrations at different times, and we're also going to calculate the AUC. So for this first part here, we're just plugging in the time values, and we're figuring out, okay, what is the concentration at this point? And as you can see right here, we have this whole list of values that we found. But doing this in Python is much similar because we can use what's called a for loop. And what you can see here is we take our v is used as our times, and for every value in v, we are creating a row on this table that you can see at the bottom left, and those numbers are the exact same as analytically, but it only required a few lines of code instead of solving algebra. And now moving on to the second part, the area under the concentration time curve. As you can see here, integration, it's not too difficult, but this can be simplified in Python. So what we did here is we imported the trapezoidal method here from NumPy. And what that does is we created 1,000 different trapezoids to estimate this value. And as you can see here, we got nearly the exact same as analytically. This method could be improved by increasing the amount of trapezoids you could use. As you can see here, we only did 1,000. We could have done, 10,000, 100,000, whatever was necessary. And that is all. Thank you.